Yeah, hello and welcome everyone. Let's start. So I'm Theo and this is Lenny, and we will tell you about our cross-platform library for encrypted messaging. So first we'll give you some introduction what Threema is. Then we'll tell you about our design and how we do the FFI bindings. Finally, we'll come to a conclusion. So Threema is an end-to-end encrypted messaging application. So EMA, and because that's a bad name, they choose Threema. Is it a better name? Well, it's debatable. Anyway, you can use this application to write text messages or voice messages or whatever to your friends and in work context. Threema has started in 2012. Back then, it looked like this. So in 2012, WhatsApp was not yet owned by Facebook, and it was not encrypted. Many people used the Windows Messenger or MSN, and Signal was still called text secure and did not allow for end-to-end encrypted group messages. So this was the time when people used Facebook Messenger to chat with their friends in internet coffee over plain HTTP, so without any encryption. That's when Threema started. Threema is based in Switzerland, and we host our services on bare metal servers. Now, basically, there are three platforms. So we have an iOS app, an Android app, and a desktop app. We have a server, and because everything is encrypted, states are managed decentrally. Now, historically, for all of these platforms, an independent codebase have grown. So we have Objective-C and Swift for iOS, Java and Kotlin for the Android app, and TypeScript for desktop. In fact, there are even more code bases, as we have some SDKs and gateway servers. As you can imagine, this comes with the problem of having three different sources of bugs. If we find a bug, let's say in the Android app, we have to check whether this bug is also there in the iOS app and the desktop. And even worse, if we found how to fix it, we need to coordinate between three different teams how we can introduce the fix. Maybe we need even bigger changes to do that. So out of this, we have realized that just writing proper specifications is not enough. It does not help us to avoid this kind of situation. So what we need instead is a cross-platform library. So we told ourselves, do we have to implement a protocol? Are you tired from all the salsa 20 dancing? Fear no more. Leave Threema, the one-stop shop for all your Threema needs. So that was our mission. And now, Lenny, how did we achieve this? What is our design?
Hello, also from my side here. Let's talk about the design. We set ourselves a couple of requirements from past experiences, and it should be platform agnostic. It should be Sense.io because we do not want direct access to files or sockets within that library. That is A, because we want to leverage platform native implementations with all the benefits like permission prompt flows, and B, because we actually need WebAssembly support. It should have idiomatic bindings to other programming languages, so it should feel almost native to work with these APIs in TypeScript, but also in Swift and Kotlin. And since our protocols are cryptographically very, very sensitive, those APIs need to be hard to misuse. What wasn't clear is, well, how could we achieve that? So the challenge that we are facing here is that protocol flows are asynchronous by nature. And while many languages do offer the async await pattern nowadays, so that is undoubtedly helpful in implementing network protocol flows because it makes it very easy to follow the code. So we were wondering, could we perhaps leverage async await? So here's the question for you guys. Who of you has used async await before in any language? Right, that's pretty much the majority of the room. And who of you has used async await in at least 4 different programming languages? Well, a couple of you. Yeah, I would say about 6 or 7. So that is the kind of challenge we would have to face here. Let's do a little excursion into async await in different programming languages. On the left, we have JavaScript code, and on the right, we have Rust code. And both have 3 print statements in here. And they basically are the same. So let me quickly explain what's going on here. We have an async function called example, and it prints something. Then we have a wait for 100 milliseconds, and then we print something else. And then we create, further down, we call this function. And in JavaScript, that creates a promise. In Rust, it's called a task. Then we print something, and only then do we await what we have created here, the promise or the future. So they should run in the same order, right? Well, not exactly. I have labeled the print statements here. So what's happening is that in JavaScript, actually, the first print statement at the very top would be printed. Only then would be the second one, which is between creating the promise and awaiting it. That would be the second one that is printed. And the third one would be after waiting 100 milliseconds. But on the Rust side, it is different. There we create the future, and then we have the first print statement, which is between that and awaiting the future. And the reason for that is that in JavaScript, the synchronous part of async functions are executed immediately before the first await. In many other languages, that is not the case, including Rust. Here we have another example, and we're looking at async cancellation here. This is Python, and it is using async I/O. Python was one of the first languages to introduce async await. And how it works in Python is we have another async function called example, and we are creating it in Python. These are called coroutines, and then we can wrap it into a task. And then we can cancel that task. This is exactly what we're doing here. But the interesting bit is that in Python, async cancellation is cooperative. We could just ignore that in the coroutine or task. We can just catch the cancel error and just carry on. Then this is also different across other different programming languages, like JavaScript has no built-in mechanism to cancel promises at all. There's a pattern using an abort controller, but not all APIs use it. So the conclusion of our exploration here is that async await is similar, but also very different across the programming language landscape. And while we have figured out that the scheduling works differently, the code execution order in particular is different. Cancellation works differently, but also we haven't even talked about event loops at this point. They are also different implementations across the programming language landscape. Each language pretty much ships its own event loop, and cross-foreign function interface task would have to be scheduled on one or possibly even both of them. And that is certainly doable, but we decided it is too much of a headache for us. There are just too many different languages involved here with different concepts, and the code still needs to be debuggable. That's already hard enough with FFI, without any async await mapping magic going on. But here's the thought. Maybe it would be an interesting concept to get a standardized async await across programming languages. Just a thought. So if we don't want to use async await, what kind of API design could we apply then? Well, to figure that out, let's take a look at how our protocols actually look like.
So a typical protocol for us looks like this. We have our client and the server. So this is the chat server, the server that's responsible to forward all messages. Now, when the app starts, the client has to log into the server and tell them, hey, I'm here and I have this identity. For that, the client sends the client hello message. The server parses it and responds with the server hello. The server hello contains a challenge in which the client is requested to prove its identity. The client does this in the login message, and if everything goes well, then the server replies with the login ACK message. So if we closely look at this, then we realize, well, we could define this as a state machine. And this state machine can then be driven across FFI boundaries. The benefit here is that we don't have any asynchronous calls at all, but the drawback is that it needs to be used correctly. So the app developers need to know how to use the state machine correctly. But if we maybe can instruct them exactly how to do it, then it could work. So we define protocol flows as state machines. How do we do that? So let's look again at this protocol. So first we have the three states. We have the server hello state, the awaiting login ACK state, and the post handshake state. In a normal, that means in a good case, it just goes through it like this. And for every transition between two states, we can clearly define what needs to happen. So, for example, to go from the awaiting server hello state to the awaiting login ACK state, the server hello data needs to come in, and the client needs to send out the login message. We can do this for every state transition, and we also have an error case if something goes wrong. Now, in theory, we could build this in our library and instruct the app developers how to use it. The problem here is then that they must know the internals of this. So the probability that they use it wrong is not negligible. So that's definitely not what we want. But we can go one step further. We can abstract this state machine as a black box state machine. For that, we give the callers a function that is called new, with which they can create the protocol. Then they basically have two ways to interact with this black box. First, they can call poll and get an optional instruction back. If there is an instruction, well, they need to execute it. If not, then they just go back and poll again. And the other thing that they can do is they can add chunks from their TCP listener. So every time a new packet arrives, they pass it over to this black box and can then poll again. With this, we can build the exact same state machine as before, with the difference that app developers now don't have to know any internals. Even better, we could change the internals without them noticing it. So if we port that to Rust, it's quite straightforward. We have an enum to model the state with all the different states here. We have an instruction that is here in this bit simplified example, just an outgoing chunk, so data that needs to be sent to the server. And we have the black box protocol that contains the state and with which the callers can interact by calling the mentioned two functions, poll and add chunks. And you see that if they call poll, they get back an optional instruction. Now, in practice, there are some more functions, some more bits and bytes here and there, because we can also use this protocol in the post-handshake state, so to send actual messages. Now, having seen this, how can we port this to FFI bindings?
All right, so how can we make the implementation accessible to the application that we are using? So we want to expose them through a foreign function interface, of course, and for that purpose, we have split the bindings into two parts. On the left side, we have the WebAssembly TypeScript bindings, and they expose the APIs to the desktop app through WASM bindgen and tsify. And on the right side, we have the Kotlin and Swift bindings, and they expose the APIs to Android and iOS through Unify, which is a neat library provided by Mozilla. Both binding layers generate code that the apps can then use, and the result is the exposed protocols are backed by our core library, libthreema, which is using Rust with all of its benefits like performance and safety. So how does it look like in practice? Here we have an example that is exposing an error, which is just the usual way we would do it in Rust using an enum. And we see 3 derive statements here. At the very first one is just using derive using this error, which is a common way to do it in Rust. And then we have the one that is only activated for the Unify feature, used then by Android and the iOS apps, where we derive Unify error. And then we have another derive statement which is only activated for the WASM feature, where we also derive something here and convert it using cert, anticipy and WASM bindgen. This is a little bit of boilerplate. Well, actually, it's a lot of boilerplate, but everything here has its purpose, and it is absolutely manageable. So here we can see how it is mapped to Kotlin code. On the left, we have the variants of the error in Rust. And what we can see is that the doc strings are nicely present also in the generated code for Kotlin. And also, more importantly, it generates a dedicated exception type, which is idiomatic way to use errors in Kotlin. That was a goal. And you can catch it accordingly within Kotlin code. Right, so here are the WebAssembly / TypeScript bindings. Here it is also pretty nicely mapped. We have chosen to use a type value format for errors in that case, which is something the clients can then switch over with a switch statement or just an if conditional. Unfortunately, the doc strings are lost here. Maybe that is something that could be improved in tsify. Right, so maybe you have noticed that we don't use JavaScript errors. And, well, the reason for that is that if we don't declare custom error subclasses within JavaScript, we can only construct generic error instances, and then we could only supply a string. So that would be a little bit annoying for the clients because they would then have to match over a string when they match different error messages, which isn't ideal. And yeah, to be honest, default error handling in JavaScript is probably not the best anyways, because you will have to look very deeply into the documentation and what can throw at which point in time. So we decided to just basically return a tagged union here, which mimics the way we are doing results in Rust, which is then just much more expressive and explicit. Yeah, and that basically sums up our bindings. Now I will hand back to Theo for the conclusion.
Yes. So what have we learned? We have learned that Sans.io is great because of 2 things. It enforces clear state abstraction. That is, we as library maintainers, we are clearly forced to think how to model states. And then it is platform independent. So the apps can use it, Android can use it, desktop, and iOS can use it. Another thing that we have learned is that it's really good testable. So we can just move our state machine to a given state and then test, is the transition as we expected? Then we have learned that FFI is tedious, yes, but the Unify crate and the tsify plus WASM bindgen help a lot. So it is a bit of overhead, but it's still manageable for us. And lastly, we should have started this project much earlier, because it's actually not too hard and the benefits are tremendously. With this, we're at the end of our presentation and we're happy to take any questions.
questions? No? Here's one.
So, nice presentation, thank you. I was wondering how large is the Rust code base at Threema, and are you suffering build times?
Build times?
Yeah.
It is not that large yet, but we are already suffering with build times. Yeah, if we could speed that up, that would be very helpful. Yeah, but we haven't really invested a lot of time into investigating what we could do to improve the situation yet. Yeah.
Yeah.
Anyone else? I have one, though. Were there other solutions that you looked at for building a cross-platform library, and what made you go with Rust to make that decision?
I'll give that to you.
Well, I investigated a little bit and looked at basically our competitors. I've seen that the Matrix Foundation is also using Unify, I think. They also try to use async await, I think. And then, of course, we have also investigated libsignal. But libsignal is C, and that probably, the reason is probably not, is that it is a pretty old library, so they didn't start on Rust for that reason, I'm assuming. And maybe they have a little different set of goals for their APIs. Yeah, so the reason why we wanted to use Rust is actually because of all the benefits, performance, and memory safety. That is something very important to us. There are very good cryptographic libraries available for Rust, which we are using. And actually, the interesting bit is also that the way we are designing the API makes it very easy Rust code. It is very beginner-friendly. Rust code, we don't need to deal with lifetimes a lot. Because they are all state machine, you can just basically put them on the stack and manipulate them from A to B.
Oh.
You mentioned you use cryptographic libraries in Rust. Are those from Crates.io, and are those audited by you? Or do you trust them?
Yes, so we use Rust crypto crates, and we recently audited or let an external company audit Rust crate for us. Yes.
Any other question here?
Do you support cancellation for your I/O operations?
Well, the way we are doing cancellation is basically by, well, for example, if we are losing a connection, the TCP connection, then because that TCP connection is provided and backed by the apps themselves, and they just hand over the bytes to Threema, the way we are dealing with that is that we are saying, okay, so if you're losing the connection, you just create a new instance of the state machine. And that makes it it is a little bit more, than having it completely abstracted away. It takes a little bit more effort. But we think it is a nice trade-off, because then we don't have to have async callbacks that we need to register and then clean at some point.
Any other talk or any other questions? No. Okay. Well, thank you so much, Lenny and Theo, for sharing that.
Thanks.